Alright, so here we have, I guess, is a really simple integer expression that I'm just going to calculate. Perhaps with unorthodox methods, with slight overcomplication. However, I do seek to obtain this mysterious answer. So, to start off, I think I will just convert this expression into something that's more usable with integration, per se. So, I know that 2 to the second power is equal to 4, and then I could just simply do 2 to the second power over 2, which is still equal to 2, plus, I would assume, I know that 3 times 2 is 6, so I'm just going to put that here. So we'll have an expression that looks kind of like this. I'm going to slightly put a little bit of variables in here, so I'm just going to create this variable called x, and that's going to be equal to 2. I'm only going to substitute a selected few of these 2's in this expression so that I can still use the entire thing. So I'll substitute this x over here, and then this one here. And then I need to convert it into this kind of notation here. This is a good thing though, because now we know what the integrated function of f of x is. So that means the integrated function of f of x is equivalent to this. I do want to find the original function, so when I do try to calculate this sum, I need f of x, not integrated function of f of x. But we know that the inverse of an integration is just differentiation. So I'm going to differentiate both sides. So we'll have something like this. You can just split the differentiation into this. And then these actually cancel out, so I'll just get f of x instead. I'm going to factor out the constants because you can do that with differentiation. So that means I'll just have something like that. Oh, 3. There we go. Okay. So now that we have this little, I guess, little equation here, I'm going to differentiate the little functions in here so that I can truly get everything without any calculus. So we're going to differentiate these to the first principle, where for all functions f, this can be anything, the derivative of f of x is equal to limit as h approaches 0, f of x plus h minus f of x over h. So first I want to differentiate x squared. So I'm going to put this exact form, but instead of f of x, I'll just have x squared. Therefore, I'll have something like, x plus h squared, or not plus, but minus x squared over h. So I'm going to just square the term here, so that'll be like a quadratic. And then these x's will just cancel out, leaving this with 2xh, or actually everything over h plus h squared. These h's cancel out on both sides, so I'll just split this into something more usable. And we'll still have h over here. And because 2x is technically a constant in this case, it's just 2x. And then we just plug in 0 for h, and we'll just get 0. So we get 2x for derivative of x squared. And then I'm going to do the exact same thing with x in this case. So instead of x squared, I'm just going to differentiate x. So it's just going to be something like that, minus x over h. These x's will cancel out again. We have our limit as h approaches 0. We'll just have h over h. These cancel out. That's just the limit of h approaches 0. 1. That's just a constant, so we'll have 1. Alright, so we can plug it back into our little equation here. to get f of x, and we know it's equal to 1 over 2 times derivative of x squared is just 2x, so we're just going to plug that in, and then the derivative of x is just 1, so 3 times 1. These cancel out, it's just f of x is equal to, I guess, x plus 3. Wow, that was nice. So now we have the original f of x, which we can then use in our integration. So in this case, because we have a 2 over here, we're going to have an integral that kind of looks like this. Or definite integral, I guess. It's not really f of x. I'll just do x plus 3. Yeah, there we go. And we're trying to find out what that is, because this is technically equal to 2 plus 6. Therefore, we're going to use something called the Riemann sum. I don't know how to pronounce it, even though I love them, whatever. So we know that for all definite integrals f of x, it's equivalent to this little sum here, where the limit of n approaches infinity. Here we go. And then we'll have I equals 1 f over the ith index of x times delta x. And we have, I guess, selected formulae here that we can then use to solve this function here. So delta x is equal to b minus a over n, and we have b and a, and then ith index of x is simply equal to a plus delta x times I. And bear in mind that I is the index in this case, not the square root of -1. So we're not going into the imaginary world. Alright, so since we have the values for all of this, we can simply just use, we can solve for delta x, which is pretty easy. This delta x is simply equal to 2 minus 0 over n, which is simply equal to 2 over n. Ith index of x is simply equal to 0 plus delta x, so we have that times I is simply equal to 2I over n. Okay, so now we have all these values, we can just plug them in. F of x, ith index of x, we know that it's just 2I over n, times delta x, which is just 2 over n. Alright, and bear in mind that these are brackets. This like this, it's just 2I over n plus 3, because we're just plugging them into f of x, and we're multiplying all of this by 2 over n. Then that means we'll be left with something that looks like we know that 2 times 2 is 4 from earlier, 4I over n, and then we also know that 3 times 2 is 6. I forgot the square here. So we'll just have 6 over n. I'm going to split this summation, or this sigma notation, into 2 terms, because we can do that, which means that we'll be left with something that looks a little bit like that. And bear in mind that this is also in the same limit, so I'm not going to disobey math laws in this case. The next thing we have to do is to, I guess, simplify the sum so that it looks a little nicer. And luckily that's possible, otherwise we'd be working with some really weird numbers. Since n is in this case is a constant, I can just factor out n. Therefore, I'll just have 4 over n squared with I over here. Plus, I'm going to put that in brackets, yeah. So we have really 6 over n, that's all a constant, so I'll have, actually no, I won't have I, I'll just have 1. Alright, so I guess to go a little further, we need to use a couple of rules. Luckily, I know a couple of summation rules, it's pretty simple. So when we have a case like, oh, that's horribly drawn. Okay. When you have something that looks kind of like that, it's simply equal to n times n plus 1 over 2. I don't know the definitive proof, but this is math. If these laws are valid and people actually use them, then they work. And if we have just a constant here in the sum, it's really just multiplication. A sum is basically repeated or I guess multiplication is just repeated addition with one constant. So that's kind of the fundamental explanation. In this case, it'd just be a times n, or an, which is quite frankly an answer. Okay, with that in mind, we can then further go into this whole expression here. And because of earlier, we can just simplify that into n times n plus 1 over 2. We can also add that to 6 over n, and we know that 1 times n is just n, therefore times n. We gotta cancel a couple of terms out to make things a little simpler, which is a good thing. So I'll cancel that out. I'll also cancel all of these out. 1 and okay. So that will leave us with something that looks kind of like, yeah, something like that. 6. Perfect. So now we have something that looks like that. I'm just going to expand the 2n plus 1, 2 times n plus 1, to obtain 2n plus 2 over n plus 6. So now that we're almost finished, I do, in fact, I might need to put the 6 into this fraction here. So I'm going to multiply 6 by n times n over n, which is still 1. So I'm obeying math laws. So 2n plus 2 over n plus 6 over n, or 6n over n. I'm going to add 6 to the fraction now that I can to get 8n plus 2 and everything over n. I'm going to slightly simplify everything here. Oh, yeah, I guess so. So the 8n will cancel out to just become 8 plus 2 over n. Okay, so now I'll just split this limit into two limits. 8 plus n approaches infinity, 2 over n. I'm going to factor out the constants. Actually, I don't really need to for this limit here. So when you have a constant with the limit is just the constant. So we'll just have 8 right there. And I'll factor out 2 from this this limit here. So I'll have 1 over the limit as n approaches infinity, 1 over n. Well, it is 0, but just for clarification, in case you don't know, I'm going to use a example where I'll do y is equal to 1 over x in this case, and we know that it will look kind of like this. It's not to scale. I hope it's feasible drawing. And we'll have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So when you increase the denominator, it'll infinitely get smaller, but it will never be 0. So when this value approaches infinity, I guess a concept in this case, it's going to infinitely approach 0. So in this case, we'd basically be doing 1 over infinity, which is essentially approximately approaching 0. So when we work with limits, we're not looking for exact values, and therefore we know that this limit's just 0. So we'll have 8 plus 2 times 0. I'm using simple PEMDAS. 2 times 0 is just 0, so we'll have 8. And I believe that's our answer. So we can then be certain that 2 plus 6 is equal to 8, which is awesome. So, okay, if I can, just with a little bit of math, I guess, you're able to convert all of this into a simplistic differential equation, solves it, then used a sum or a Riemann sum to essentially calculate the definite integral into something that's feasible and, I guess, correct in this case. I mean, if you plug it into a calculator, I would assume it worked. 2 plus 6 is equal to 8 after all. Regardless, that's a significantly better iteration of my previous video, where I do actually know how to do calculus to at least a basic level, of course. But Yeah, I've overcomplicated it in a feasible way where I didn't hurt my brain too much, but still, I hope it's understandable in the way and the methods that I did it.